You know, they're everywhere. In your car, your computer, the power plant that keeps your lights on. Pretty much any machine with moving parts has them. And yet, we almost never give them a second thought. So today, we're going to pull back the curtain on the hidden world of one of engineering's most vital components, the bearing. We'll start in a small workshop, watching one get made with incredible precision, and then we'll zoom out to see the insane demands of heavy industry. And I just have to start with this quote because it's perfect. It just captures the whole can-do, get-it-done spirit of a real machine shop. See, we're not starting with some dry textbook theory. Nope, we're jumping right into the trenches with the metal chips flying to see how one of these amazing parts is born from just a raw chunk of metal. So our story kicks off with the creation of a single, highly specialized part called an aerostatic bearing. And look, this isn't something that just rolls off a massive factory assembly line. Oh no, this is a feat of custom machining where every single cut, every single measurement has to be absolutely perfect. Okay, so it all begins with a simple rod of aluminum. First thing you do is face the end, which is just a fancy way of saying you machine it to be perfectly flat and clean. Then you rough out the outside diameter to get it close to the final shape. Next up, you drill a hole right down the center. And finally, the magic touch. A special tool bores out that hole. Carefully, slowly, enlarging it to its final dimension with an accuracy that's just a fraction of a human hair. Every step is about taking away material in the most controlled way possible. Now here's where it gets really cool. After all that high-tech machining, you get to a point where you need a perfect little nest, a spherical seat for a mounting ball to sit in. And the solution isn't some super complex computer-controlled cut. It's actually a clever, kind of old-school trick. And this quote explains it perfectly. You literally take the hard steel ball that the bearing will pivot on, and you just press it into the softer aluminum. It's like brute force meeting surgical precision. It actually deforms the metal, creating a perfect custom-molded socket. This simple little move gives you a massive contact area, which makes the whole bearing way more stable. It's just brilliant. All right, so we've seen the incredible care it takes to make one of these things, but how does it actually work? I mean, what's the big idea? Well, this clever little device literally floats on a cushion of air. So let's break down the parts. You've got the aluminum body, the main structure we just saw being made. Air gets pumped into an internal chamber, the plenum, and then it seeps through this special porous graphite insert. Think of the graphite like a sponge, but for air. It lets the air escape super evenly, creating this thin, stiff cushion for the bearing to ride on, completely friction-free. And that ball mount we talked about, that lets the whole thing pivot so it can align itself perfectly. And hey, let's demystify one of those terms right now. You hear the word plenum thrown around in engineering a lot. It sounds complicated, but it's not. It's really just a fancy name for an air chamber. Its only job is to take the air coming in from a hose and let it spread out evenly before it goes through the graphite. Simple, right? But absolutely critical. Okay, so we've just obsessed over making one perfect tiny bearing in a workshop. Now I want you to take a huge mental leap with me. We're leaving the quiet of the custom shop and we're entering the roaring world of giant turbines, massive compressors, and power plants, a world where the stakes are, well, astronomically higher. And this brings us to the big question, right? That beautifully crafted little part is amazing. But what happens when you need it to work inside a multi-million-dollar piece of industrial machinery? What kind of life expectancy are we talking about? A few months? A year? Get ready for this. The answer is just staggering. In big industrial plants, they expect 6 to 7 years or more of continuous 24/7 nonstop operation before they even think about shutting down for maintenance. The bearings inside those machines have to survive under crushing loads and incredible speeds for almost a decade. This quote just nails the fundamental problem for engineers. I mean, theoretically, if a bearing is always floating on a perfect film of oil or air, it should never wear out. It should last forever. But, as the man says, none of us live in a perfect world. Reality always finds a way to mess things up. So that reality leads to this really important design philosophy. Engineers actually design bearings to be the sacrificial elements. They're meant to be the first thing to fail and to fail in a predictable way. Why? To protect something way more expensive, like a gigantic turbine rotor. They're basically the Secret Service agent designed to take the bullet for the president. So if failure is literally part of the plan, you have to understand it inside and out. What are all the enemies that these industrial bearings are up against during that 7+ year tour of duty? Let's dive in and look at the anatomy of a failure.
And man, the list of things that can go wrong is, well, it's long. You've got the material itself just getting tired, that's fatigue. You've got damage from tiny little dirt particles in the oil. You've got chemical gunk like varnish building up. You've even got rogue electrical currents. The threats come from everywhere. They're mechanical, chemical, and even electrical.
Let's just zoom in on two of the sneakiest threats: electrical damage. You can get electrostatic discharge. Think of it like a tiny lightning storm inside the bearing from static buildup. It can leave the surface with this weird frosted look. But even worse are electromagnetic currents, which can be generated by leftover magnetism in the parts. These can create enough energy to literally weld tiny spots together and then rip them apart. Nasty stuff.
Now, one of the ways engineers fight back is completely counterintuitive. Many bearings are aligned with a soft material called babbitt. And you'd think, logically, a thicker layer would be stronger, right? More material, more strength. Nope. It's the exact opposite. This chart shows that a thin layer, just 0.005 of an inch thick, can last more than double what a layer 3 times as thick can. In the world of bearings, thinner is actually stronger.
And if you thought that was a big deal, just look what happens when you add heat into the mix. The bearing's lifespan absolutely plummets as it gets hotter. Just going from 200 degrees to 300 degrees Fahrenheit, which is totally normal in these machines, slashes the bearing's life by over 70%. Heat is the #1 enemy, period. Okay, so we've seen the problems. We've met the enemies. It's a tough world out there for a bearing. So how on earth do you engineer something that can survive this gauntlet for years and years? Let's switch gears and look at the solutions and an absolutely fantastic real-world success story. Well, the keys to a tough design fight back directly against all those failure modes we just talked about. Engineers use clever designs like tilting pad bearings that can adjust on the fly to changing loads. They use that super thin babbitt layer to fight fatigue. They use ball and socket pivots, just like in our little air bearing, to handle any misalignment. And they do a ton of complex analysis up front to create a system that's just naturally stable and doesn't want to vibrate. So, does all this theory actually work out in the real world? Let's take a look at a case study. We're talking about the huge compressors at an ethylene plant run by Nova Chemicals, where they put all these robust design ideas into practice. So remember that goal we talked about? That 6 to 7 year target? Well, after they installed these advanced bearings, the compressors at this plant ran for 9 years. 9 years! Without being shut down for a single bearing inspection. That's just an incredible win for reliability. But wait, here's the real kicker. This is the most stunning number of all. After 9 years of nonstop work, they finally opened the machines up to see how things looked. And the worst amount of wear they found, the biggest increase in space between the parts, was just 6/10,000ths of an inch. To put that in perspective, that is about 1/5 the thickness of a single human hair. It's almost nothing. It is a mind-blown testament to brilliant engineering. So there you have it. From the painstaking, meticulous craft in a one-man shop to the epic durability needed in a massive factory, bearings are truly the unsung heroes of our mechanical world. They just do their critical, invisible work day in and day out for years on end, flawlessly. Which kind of makes you wonder, doesn't it? What other hidden, brilliant components are out there quietly keeping our entire world in motion?